Let's welcome Professor Richard Harper. He's originally trained as a sociologist, but now a computer scientist. He's concerned with how new technologies shape us and how we in turn shape our technologies. I'm sorry, maybe the student have to turn off the microphone.
Yeah.
Okay, again. In the space that is often known as human-computer interaction, or HCI, he had written 13 books, including award-winning Myths of the Paperless Office and Texture, Human Expression in the Age of Communications Overload. He had also published over 170 scientific articles on topics covering a wide range of topics, from the social impact and design of mobile phones, to the future of search engine, to the latest incarnation of artificial intelligence, the role of video-mediated connections in family life, and even on the use of big STEM in technology design. So let's welcome Professor Richard Harper to give us a talk. Thank you.
Good morning. Let me share my slides.
Okay.
Okay, so good afternoon, everybody. It's my pleasure to talk to you. My first slide just gives some example of some of the things I've written over the years, from studies of the role of paper in computing, through to more recent studies which have looked at the problem of choice and how we understand choice, and that's bound up with how we understand what AI might do for us. Can I have the next slide, please?
Okay.
Yeah. I'm going to go a little bit fast because we are now using that time. So I'm concerned primarily with human-computer interaction and what role it might have in what I'm calling the age of AI. And part of the problem we have in HCI research is we're dazzled by what AI can do. So I'm going to talk a little bit about why we get dazzled. And then I'm going to talk a little bit about the kind of purposes that we should be focusing on that HCI can enable through good design with AI. And I'm going to talk about some basic concepts like abstractions and grammars of action and provide some examples of that. So if we can just do the next slide quickly, please. So my talk is about HCI, not artificial intelligence, or rather it's about what you can do with AI and where we can take AI with the perspective of human-computer interaction. So next slide, please. The trouble, as I said, is that I think human-computer interaction researchers, and I think designers too, a lot of researchers who are not in the AI community get dazzled. So I'm going to give you some examples about that. So at a big conference in London called Hoxton AI, in Hoxton is a fashionable district in London where many of the new companies, artificial intelligence companies, are based. So the biggest conference in England is called Hoxton AI. The opening address at that conference was the presenter stood up and said, anybody who does not understand or recognize this algorithm should not be here. And that algorithm is Bayes' algorithm. And people inside artificial intelligence not only think that Bayes' algorithm is the most important algorithm that's ever been invented or the most important equation, they also think that Bayes is how the human works, that how the mind works, functions in much the same way that Bayes' algorithm does. Now, that's their religious belief. It's not true. But what it results in human-computer interaction researchers being asked questions like whether we think AI is real, which to me is a silly question because clearly AI is a functioning tool. Whether artificial intelligence equals people is a separate question. And we asked, will it happen? Are machines intelligent? How do they work, machines? That is, how we people, are we really like AI? And those questions, I think, stop us thinking properly about what we can do with HCI. Can we have the next slide?
Okay, sorry, 顾若雨记忆一下。好，大家都记忆一下。
我已经
Okay, go ahead. Okay, sorry, Richard Harper, go ahead.
Can I have the next, can you scroll down to the next one?
Okay.
Please. So I think for good HCI research, we need to relearn how to look. We need to stop being dazzled, and we need to think about what you can do with HCI. And I think the best way to stop ourselves being dazzled is to remind ourselves, and for some of you this will be new, to learn what some of the essentials of HCI are. Can we have the next slide? The essentials of human-computer interaction is to design a combination of the powers of computing and the aspirations of people, and to make those new purposes through that amalgam, through that mix. And that should be our passion. Our passion should not be people, it shouldn't be computing, it should be how you can bring those two together to let the two achieve something. And we should be passionate about that. For the next slide, please.
Yes.
But the trouble we have in HCI research is we don't really know what AI can do. We are dazzled by things. It's too complicated for us, we think. The AI researchers tell us it's too complicated. The language used to describe artificial intelligence is often opaque. And even AI researchers themselves use the phrase that their technologies, their tools are black boxes, by which they mean inside the computer, it is so complicated that no one can understand what goes on inside. It is as if it's a black box that a magician has and magic goes on the inside. We can just see the news slide. So these are examples of all the phrases that are used to dazzle us. They describe different ways of doing artificial intelligence, but they confuse us. So one consequence of that is that some researchers say that AI needs explaining. In their view, explanation should come before one figures out what to do with AI, that ordinary people need to understand and be explained what AI does to them before they start thinking about what they might do with AI. And in the US, the major research funding agency called DARPA funds a huge research program called Explainable AI. Move to the next slide. I think this is a really bad idea. I would say no to explanation, or rather that in human-computer interaction research has shown in the past, good HCI has shown that explanations are only sometimes needed, not every case. And I'm going to provide you with a canonical example in a minute. I agree that AI is complex, but the complexity or the explainability of that amalgam of computer and machine are only relevant or important when the purposes are defined. And not all purposes require explanation or solutions to complexity. So can we have the next slide now, please? So let's look at some old examples in HCI of purposes, and hence examples of when explanations were needed, or perhaps when they weren't needed. So let's just pause here. Does anybody, I know I'm not going to be able to hear, does anybody know what that machine is and why I've selected that machine as an image? Min might know this. That's a photograph of the world's first ever WIMP-based networked machine. It's a Xerox Star. Everything you see in the machines you see on your desktop now, including most of the fundamentals in terms of engineering, are based on that machine. And that was designed at Xerox PARC in Palo Alto, long before if you like, the digital revolution. And perhaps most importantly for now, on the right of that image, if you look at the slides, there's a file icon. And what I want to, whoa, hold on. What is underneath a file icon in this example? Now go to the next slide. Data for a file, so take say a Word file, a word processing file. The data for that file, when it's stored on a PC, it's broken up into different parts and it's allocated to different areas on the disk of the PC, because storing data is much more efficient if you break it up and put it in different parts where there's space. If you save a file in one place, it can be very inefficient. A much more efficient way of doing it is to allow it to be broken up in different sorts of places. But when a user clicks on a file icon on the desktop, all the pieces of data are brought back together from different places on the disk, so that a user can do things with the single file, the file. They don't interact with pieces broken up in different places. They interact, what they understand with is one file. So they do one click on one file, and one set of data, one set of text, if you like, shows itself on the screen. Does the user understand all the complexity underneath? Does the user have this explained to them? The next slide. No, it is not explained. What the user does is only simple, one thing. They point with the pointer with the mouse, and they click with the mouse. And when they click, they're doing something with the file. They don't need an explanation. What they do need is a representation of the file that lets them do that. And that representation is called an abstraction. The abstraction unifies the doings of the computer with the purposes of the user in ways that makes complexity and explanation, in this instance, irrelevant. The abstraction is part of is part of how the computer system understands itself. It has a higher level definition, an abstract definition of what a file is, and underneath that abstraction, it also has a separate set of definitions for where the files are stored. But it understands that the abstract level is where it should interact with the user. So at the point of abstraction is the point of interaction. The abstraction has to be nicely designed. Well, stop. The abstraction enables the aspiration of the user and the function of the computer, so they work on a joint purpose. It constitutes, as I'm putting here, the explanation for both the user and the machine. In this instance, the abstraction for the file is bound up with the notion that the file is a document type, like a word processing, and the abstraction enables the user and the computer to work together around drafting, creating a document, editing a document, storing the document, printing the document, sending a document, and revising it. And these terms are write, read, write, store, post, print. They're all on a file. Next slide. Now, this is a single example. There is no universal abstraction. And by the same logic, there is no universal explanation, which is what some people in the AI community seek, for example, DARPA. In HCI, we've learned long ago that there is no such thing as a universal explanation, because there's no such thing as a universal abstraction. There are only abstractions for particular purposes, and some of these purposes require explanation, some don't. What they depend upon is another concept, which I'm going to talk about now, which is called a grammar of action. Can we have the next slide? A grammar of action is a term used to describe the essence of some activity. So the grammar of a computer game can be, for example, a hunt and shoot game, where the individual tries to find a destination target, something to kill, or the grammar of a computer game can be a collaborate and play. And a collaborating play game is where the first thing you do is you make a team, and then your team plays against another team. So the grammar of action for computer games is a way of summarizing the essence of the game. The overarching grammar defines how particular actions are done. So if I take the first example, a hunt and shoot game, the first thing in that grammar of action for that game that should be done is one should be able to find a gun and then shoot with it, for example. So the abstractions of the computer game should reflect that. They should let you, for example, in the first instance on a shoot and hunt, find the gun. You do not find the hunted thing first, you find the gun first. And then you need to be able to do things with the gun which lets you hunt. So purposes, computational actions, the abstractions which allow those purposes for the user and the computer to work hand in hand are defined within different grammars of action. So next slide, please. When Xerox, the Xerox PARC, defined the file abstraction, they were emphasizing, or they emphasized, the grammar of text creation and editing. The abstraction that we've talked about earlier created that kind of grammar, the kinds of doing relevant to text creation. Now, clearly, that's long ago, and that's a grammar we're taking for granted. If we can see the next slide now. There are lots of grammars of action, and some use AI. These do lots of new things, new forms of activity which require new abstractions inside these new grammars. So let's take an example of a grammar of action with social media. Let's take an AI number one. Let's take the fundamental AI algorithm in Facebook. Can we go to the next slide, please? That algorithm is used to articulate means to express or to define nearness. So if you post some content on your Facebook page, that post is displayed to those that the algorithm defines as being near to you. It does not post to everybody on Facebook, but only to those near. The algorithm expresses nearness, if you want to put it in technical terms. The algorithm is often called edge rank, and that's because nearness is calculated by the algorithm as a distance between edges on a graph. And that's a funny way of defining what it means. It's a very ancient algorithm, in fact, devised in the 18th century. But could you show the next slide, please? The important point is that when the human posts on their Facebook page, they think, and they indeed are posting to friends. They're not posting to strangers. They are posting to those near you. And I put near in inverted commas here because the near is an abstraction. It's what the computer thinks you understand as near and what you think, but they touch, but they're not the same on either side. The AI algorithm calculates who is near for you. And so when you post, it displays your post to those near. The abstraction is in a post allows the user and the system to work together. That's the abstraction inside the grammar of action. But now listen, this is what you need to understand. The abstraction also knows that when you are posting, you are not sending content, you are not giving content. If you send content, you no longer have it. So you're giving it to your friends and they have it. You cannot post it. You're not posting on your webpage. They have it. They might want to post it. If you give it to them, then likewise, you wouldn't have it yourself. So posting is a kind of showing or displaying. And it's showing or displaying to a particular set of people that you know will be looking, not strangers. Go to the next slide. It's not a perfect or well worked out grammar. What this algorithm, what Facebook's edge rank algorithm understands as nearness does not match. It's not exactly the same as what people understand as nearness. To the Facebook algorithm, it's a mathematical function, a derivation, as I say, of edges on a graph, but essentially a question of distance, of mathematical distance, a mathematically constructed distance on a great big graph where they have, on that graph, there's different points on the graph and those points are persons. And there's a measurable distance between those points. To people, nearness is not a mathematical thing. Nearness is an emotional thing. So that So one might be near to someone, but never see them. So for example, how often do you post something to your partner? I never post anything to my wife, for example, because she would think that very, very weird. So my actual emotional distance is different from my real distance, if you like. And one of the problems with Facebook is that the distance that it creates in edge graph doesn't exactly map the emotional distance I have with people I live with and my close friends. But if we can do the next slide. The things you can do on Facebook do let you do interesting things, but they also beg certain sorts of questions. So I've given you some example, an oddities. So what is the relationship between the files you post and the files you keep on your own machine? If you post something on your machine, do you also keep it on your machine? Or when you post it, do you no longer keep it? Do you curate a post? Do you look after it? Or when you post it, do you think Facebook should be responsible for curating it? When you unpost something, do you keep a version of that on your machine? Or do you delete it from your home machine? Do you want everyone else to remove the copy of the post? I'm pointing out some aspects to do with what you can do with the Facebook abstraction, the nearness abstraction, what it doesn't let you do clearly, but nevertheless, it does let you do things together. And one of the things you might say, obviously, is the case that Facebook does okay. People make do with the AI nearness and laugh at the oddities, but they leverage the possibilities. They understand enough of the grammar of action to do the things you can with that abstraction. And the abstraction is good enough for a particular grammar. So can we see, next slide, please? So with Facebook, you can see how AI computation and users' aspirations can work together. But one should also note that nearness and the abstractions articulating nearness, they don't need to make you feel dizzy, and they're not difficult to understand. The abstraction for nearness is good enough to make a business. The grammar of action makes sense. So next slide. There is a moral, I think that's important for students of design and HCI researchers, that to design with AI requires one understand what the AI and the users want to do. The designer needs to see how these two, the AI function and user, can be brought together. And my point is the grammar of action needs to be invented that binds both. This might require new abstractions at the heart of what I'm calling HCI here, abstractions inside the computer and inside the grammar of action. In human-computer interaction and in design, we should know a lot about user needs, but we might not know much or enough about AI. So let's look at the next slide. So let's just look at other types of AI, how AI works. And I'm going to choose an example which is, by AI engineers' own admissions, thought to be a difficult type, and see how difficult it is, how intimidating. Is it beyond understanding? Next slide. I'm going to talk about backpropagation. And backpropagation is one of those terms that's described as the techniques that go inside the black box, that are so complicated that no ordinary person could understand them, and that even some AI engineers don't understand them. It's a technique used in what's called multi-layered inquiries, in what used to be called neural net, but these days are more often called deep learning techniques. And as I said, are often function like a black box. So let's have a look at that. And Mike, what I want you to do is try and explain how it works so as to persuade you that you can understand even the most complicated things in AI, like backpropagation. So we'll see the next slide. So let's see how the technique can be used in a task of visual identification. So if you have an image, it could be a webcam image, it could be a digital photograph, it could be images to post it on a Facebook page. Can you use this technique, backpropagation, amongst other techniques in AI, to recognize something? And let's choose an example. let's take an example of an animal. We have some images of some animals or an animal, and we want to see if the AI tool can help us distinguish whether this animal is a wolf or a dog. So next example. So that's the image, and we're going to ask the AI in theory here, could it tell us if that is a wolf or a dog? I hope you all understand what the difference between a wolf and a dog is. I'll tell you at the end of the talk, but anyway, you can see the next slide. How would AI answer the question, dog or wolf? Next slide. Using a back propagation approach, the data is broken up into parts or segments on the screen, and each segment is analyzed for what is called an identifier or summary, a classification of that segment. In the first layer, the first stage of analysis, this is what happens. So next slide. So in this instance, what happens in the first step of back propagation is that the image is broken up into a number of zones, as you can see here. So we have a number of boxes, and each box is analyzed separately. So the top left box is analyzed for whatever objects are seen inside of it, and the second top right is also analyzed separately. All the boxes are analyzed separately. Can we see the next slide? The classes selected out of each of those segments are then added and a sum made, or rather this process continues until a sum can be made, and this is called a moment of convergence. This sum is used to re-examine the segmented data to test the classifiers found in a second layer or a further run through. So this is done endlessly until the system calculates what the best fit convergence has been reached or has been. Can we show the next? So if I was to do that here, the sum is made by saying count all of those boxes which are white, and then count those boxes where it is not white. And so, for example, if you see the top left image of where the dog is, the balance of that one would say this is not probably just a white phenomenon, there's something else there. The top middle box with the dog or the wolf looks as if it has some kind of an animal with an ear. So the AI algorithm would add all those different interpretations and then come up with a balanced probability of what they think all of those different boxes add up to. Do the next slide. What is the sum here? Crudely speaking, the white boxes have it. Now, that's a phrase meaning is to win. There are more white boxes than there are other things. And the sum for the back propagation technique would say that therefore, the AI would say, let's choose an animal or recognize an animal that's most likely to be found in snow. What kind of dog or wolf, what kind of animal will be found in the snow? The analysis converges on the notion that the landscape largely defines which animal it is that's seen in the landscape. The next example. And this is Bayes' algorithm. The Bayes' algorithm actually says, is it a wolf or is it a dog? Bayes' algorithm would do the summing. Next slide. And it's a wolf, since a wolf most often lives in snowy places. So the creature in the middle is identified not by the images around the creature itself, the animal, the dog or the wolf. It's measured by the combination of analysis of that against the analysis of the other segments. And the other segments turn out to be more important than the segments of just the dog or the wolf. The other segments, the white ones, weight more than the ones defining the animal in the middle. Next slide. The important point here is that the AI tool is incredibly effective. It does give an answer, and that's quite an achievement. There might be what's called overfitting, and overfitting basically means that perhaps too much emphasis has been given to the white and too much credibility to selecting animals that live in snow as being the ones found. And when that's not the correct answer, so that's sometimes called an overfitting, or an overfitting means overemphasizing one set of data against another set of data. Next slide. The important point is that it's not difficult to understand backpropagation. It also should be clear that in AI, truth doesn't matter. Artificial intelligence is not about understanding, it's about likelihood. But a likelihood doesn't necessarily mean a wrong thing. Likelihoods can often be true things. One needs to fit or match the types of likelihood to the real circumstances. And then you need to think about the grammar of action in question. So if we're using a likelihood here to identify an animal, are we using the right type of likelihood to fit the grammar of action in question? Now, oddly, what I've done here is given an example of a grammar of action without explaining the grammar of action. I've not suggested when you would ever be in a situation where you would be looking at an image where it's mostly snow and there's a creature in the middle. What would be the situation where that would be at the grammar of action when you're in a world looking at a place where there's lots of snow and see an animal? Let's look at the next slide, please. Does the technique fit for the context of skiing? When you're on a ski slope, is the grammar of action suitable for that, or would the grammar of action be suitable for identifying dog breeds? What is the right sum? Should I say that a balance should emphasize the landscape or the figure shape? In the example I've just shown you, it would seem more likely that the landscape is the emphasis that I should be seeking. So if I'm a skier, I would be more interested in the landscape as a criteria. Whereas if I was a dog breeder, I don't care about the landscape. So you would need to choose between the types of sums to fit the kinds of grammar of action. Next slide. So in this example, I'm suggesting it is the landscape where the animal is seen that helps define the answer, what kind of animal it is. Therefore, the grammar of action that would be applied for that technique is one where the user is interested in the landscape and the animal. A skier would want to know what kind of animal would be found in a snowy area and whether it is likely to be a wolf. That fits their need, and the AI can answer it if it emphasizes that balance. If its abstraction says, include landscape when you analyze and try and identify the animal, that reflects and creates the right grammar of action. Next slide. This method would not be any good for an animal breeder. An animal breeder is not interested in landscapes, so they would prefer an analysis that compares different animals. This might also mean that the kind of data they use, the kind of example, is not one that they would in fact prefer. They would not want a picture of a single animal in a field of snow. They would want pictures of lots of different animals. Next slide. One needs to fit the AI process to the task at hand, the user task, and make sure the right data is used in that process, and then the right AI technique. But backpropagation can be used for different tasks and fit in different grammars of action, but it's the same technique. That produces the right grammar of action. So next slide, please. AI researchers have been taking on this fitting task. They've been saying, here's an AI tool, here's a backpropagation technique, and they've been giving it to users with their applications. They've been mapping the AI techniques to the grammar or the purposes at hand. And I think that's a mistake. I think HCI researchers should take on that task. They should fit the AI to the user need. They should tell the AI engineers what the AI engineers need to do. They should not let the AI engineers tell them. Next slide. Why? Because HCI researchers are trained in what people and systems can do, and AI researchers most often are not. They are primarily trained in data analysis problems. They are not trained in why those analysis problems are being investigated. But for HCI researchers to do a good job, they must come to understand what AI can do, as well as they understand what people can do. There are many different things that AI can do and many different ways that AI can work in those contexts. The nearness algorithm in Facebook is nothing like the deep learning type algorithms used in visual search. How they work and what they can do determines the kinds of grammars of action they can handle. Next slide. Therefore, HCI researchers need to learn about AI, and they need to be able to characterize how AI works. Now, characterize is possibly a strange word. It means to see how the intelligence in Facebook is, for example, something to do with nearness. To say that EdgeRank is a nearness algorithm is to characterize the algorithm. In visual search, one can say it is a balance between lots of things seen and not just one thing, is to characterize a visual search algorithm as seeing what an animal is by reference to the context in which the animal is seen. Now, I'll end now with the characterization. I showed you at that front the Bayes algorithm. Now this is the PageRank algorithm, which all of you use a version of every day, thousands of times. When it was patented 20 years ago, it was not called artificial intelligence. Google and ABC, the company now, who own Google, now relabel it. They call this an intelligent algorithm. What does the algorithm, what is it about? Let's look at the next slide. It's really important that you understand, if you wanted to characterize PageRank, one of the things you need to say is it's not about content. PageRank, and hence Google search, knows nothing about what is in some web page. There might be other algorithms which search content, but PageRank does not. It's only an analysis or an algorithm about traffic or movement by users between one page and another, and the likelihoods of traffic. And on the basis of that, what you can predict about different behaviors. So it starts with the presumption if every page on a website is equal, and then discovers where in practice people go, to discover that some pages are more likely to be gone to more often than other pages, and then uses a notion of probability to prove that, and gives the pages which are most frequently visited more weight in a map, and the pages with more weight are given more credit, more importance. It's not an intelligent algorithm about meaning, it's an intelligent algorithm about traffic. So if you characterize the PageRank algorithm thus, what would be the good grammar of action that would combine that with a user need? So what's the answer? Next slide. Think about it. I've alluded to it. It's saying that when you search for something, a good way of giving you an answer to your search is not by saying, I know what's in the content, by saying most people go to this destination when they ask this question. The trick for Google was that when it started off using PageRank, it had no data. It needed 2, 3, 4 years of data to start saying, using PageRank to say, if you're looking up Richard Harper, most often the people you want to look at are the Richard Harper in Lancaster. It's not the content that matters, it's the frequency that matters. And that turns out to be a really good abstraction for the grammar of action of using search engines. It also means that if you are my age, when Google first went on the market and offered its search engine, it wasn't very good because it didn't have enough data to make the PageRank algorithm useful. But what I wanted to show, you can have the next slide, is that to understand what you can do with AI, you need to understand what people want to do, and you need to see how AI can fit into different types of human-computer interaction. And if my argument is right, I think the future of AI is HCI. It's not AI. In other words, HCI is where the action should be in the next few years, not inside the black boxes, not by AI machines. It should be people like yourselves researching what you can do with AI. But to make a success of that, you need to understand AI. You need to get inside the box and characterize the different things it can do, and then fit those to the kinds of grammars of action that people want to undertake, the kinds of doings in the future that they want to undertake. Next slide. And that's the end of my talk. And we are about 5 minutes later than I expected. So thank you.
Thank you so much, Professor. And actually, I sent your presentation slides yesterday to our students in case they cannot understand the English well. And after that, I've received many questions from them. And now there are so many students asking some further questions for you. And I forward the question to the Dean Talk group. You can check it. Would you please select 1 or 2 questions to answer? Can you see that?
Okay. I'm just wondering where the on this system is the team talk, because I'm screen sharing at the moment, so I'm seeing your screen.
Here. Okay. Let me turn off the. Okay, I will ask the students to ask you directly. Okay.
Okay.
First one. 李忠磊同学，请你打开麦好吗？李忠磊同学。
Hello. Seriously, could you hear me clearly?
Yes.
Need I to open the camera? Is anybody here?
Yeah. 你把你的摄像头打开好了。
开了呀。
你把你的摄像头打开。
哎，是哦，我知道了。哦，是这边，这样是不是可以？可以了吗，老师？
没事，你先问吧。你开始问吧。
Oh yeah. Firstly, thanks, Professor, for the inspiring speech, and the network is not so good. We are happy to see you at the beginning. I have a question. Do you believe that the computer can generate its own operating system, like the thing in our robots? And by that time, the role of HIC may be only providing a starting point and an end point, or just providing guidances. Will that area in which teaching computers like teaching children come? Thank you.
Yes. Can I ask to a little bit of clarification? Do you mean will AI techniques learn enough to be able to teach without human-computer interaction research? Is that what your question is?
Well, it's more like the computer can learn itself. It can, like, you give it a point A, and you need it to come up with a plan B, and it can do it by itself. You just need to give it or give him a guidance, which way it will choose to go and to the destiny. You mean?
Yes. Okay. No.
Yeah.
Okay. I do understand the question. I think one has to understand that AI techniques can only answer one set of problems or one problem, and they can learn how to solve that problem in new ways. But they only learn from one set of problems. So they will own a vision algorithm and a machine learning technique for identifying types of dogs will never be able to do anything other than learn types of dogs. But it will be able to analyze new examples. So you can give it new creatures, and it will be able to distinguish those new creatures from dogs. But that's all it'll ever be able to do. So you need to understand that AI tools are, in the end, always rather narrow. It's not a bad thing. It's just that's and if you think about it, that's how all tools are. It's AI. Best to think of AI as a tool, or rather a bunch of tools. And you have to think about what those tools can do, and sometimes what several sets of those tools can do. But when you're thinking about teaching, say, children, there's no one tool that's being deployed. There are many tools, and some of those tools are never going to be computational tools. So, for example, one of the things that children learn is the art of listening to teachers. And to listen to a teacher is not a computational problem. It's a problem of respect and honor. And that's not something that AI techniques are going to be able to enable. That's not the kind of grammar of action that AI technologies can do. But AI technologies can help, for example, provide good maths examples and help teach children through iterations of, say, some advanced mathematics or even simple mathematics. But some things in the classroom, some tasks are not going to be solved by AI. So the important thing is from HCI researchers you have to be confident, and you have to tell AI engineers that their tools can only do some things, and you need to understand what those some things are, and then find out where those some things can find a good place in the classroom or somewhere else.
So in your opinion, AI is no more than codes and grammars all the time, right?
Yes, exactly. But it's very powerful. It's fantastic, incredibly useful things you can do with it. There are other things that you might want to investigate. For example, deep learning, for example, uses enormous amount of energy and enormous amount of computational power. So one of the things you might say is that with AI, although it's incredibly powerful, actually we might be using artificial intelligence to do things which are worth it. So in that example of the dog or the wolf, there are a lot of computational power would have been used to distinguish what kind of creature that would be, a wolf. And you feel like saying, why do I need artificial intelligence to do that when I can do it? When AI requires huge amount of computational processing to solve those sorts of problems. So we should be also thinking about the value of AI and not just the role of AI. And when the value of AI is how much effort is put into using AI to solve some problems.
Yeah, I got it. Thank you very much.
Thank you so much for the time. Maybe we just have one question left. So next,冯佩文同学. Okay.
Can you hear me and see me?
Yes.
And I will tell my question. Firstly, thanks, Professor, great lecture. And I have a question. Will all future trends be guided by designers or technological changes?
Sorry, can you say that question a bit slower for me?
Oh, okay. Will all future trends be guided by designers or technological changes?
Trains?
Yes, future trends.
Sorry, I mean railway trains.
Will all future trends be guided by designers or technological changes?
Let me explain again.
Yeah.
The question is about the future will the future changed by designer or changed by the technology? Yes.
Oh, I see. Okay, yeah, no, okay, yeah, no, but I think the future is changed by everybody and technology. So designers can change the future, but designers need materials to change the future, and the materials are in technology. And the designers and technology work hand in hand, and they change each other. So AI is a new resource for designers to create new possibilities. But the new possibilities that designers create can also shape what technology can achieve. But I think one of the things that you should appreciate as designers is that certain human needs and human practices are very fundamental, and they don't change that much. So to understand the basics of human nature will also teach you that the future won't be so different from today. So friendship will be the same, love will be the same, parenting will be the same. People being taught by listening to lectures and asking questions. These are not new things. These are ancient things. So the Romans did this, and in ancient China, they taught the same way. So some things do change, but much more slowly because they're more profound. So that's if can we show you that little video at the end of my slides, so I can end up on that.
Okay, thank you.
Yeah. There's a click through at the end of the slides to a YouTube clip at the end, the bottom of the slides.
Thank you very much.
If you just play that, or click on there. And this is a good example. If you just bear a minute, if that can be will it show?
I cannot play that. Sorry, but
okay.
I will forward this link to our students. Okay.
Okay. But if they play it, what they will see is they will see an animal playing, and when you see the animal playing, you will start thinking that something that's deeply persistent about dogs and people, animals and people, dogs and people, is that they play together. And as it happens, what defines a dog from a wolf, and particularly certain types of breeds of dog, for example, a husky from a wolf, cannot be defined by the visual field. You cannot see the difference. The difference is only in wolves cannot be trained and will not be trained and will not be tamed by people. Dogs will be tamed by people and will play with people. So my example of using AI is ignoring something, which is, in some examples, it does not matter what something looks like. You cannot tell the difference. The only way you tell the difference is what you can do with that creature. So with a dog, you can play. With a wolf, you cannot play. Thank you.
Okay,
Thank you. Thank you so much for your answers to our students, and thank you so much for designing this great course to our students. And I think for the time is very limited, and I hope we can have the further communication with you in the near future. And welcome to Hangzhou in the near future. Thank you. Thank you so much.
Thank you. Bye-bye.
Thank you. Bye.
Bye.
Bye. Bye.